Our speaker today for the Math Interest Group is Thad Gabara, giving a talk on Cantors Infinities. Thad has given a number of talks for the old guard in the past. One was his experience on using Raspberry Pi, which is an ARM computer, on a small circuit board. This is a popular project for the electronic hobbyist, and we gained quite some insight with his demos. The other talk was his experience using a computer graphic imaging program called Blender to design a quick cleaning cat litter box. He's a retiree of AT&T Bell Labs and has worked as a patent agent. This is the first time he'll be giving a talk for the Math Interest Group. So please welcome Thad in giving his talk on Cantor's Infinity.
Thank you, Walter, and hello to everybody. Good morning. Today's talk is going to be Cantor's countable and uncountable infinities. What I'll do is I'll give you the background. We'll take a look at Cantor's background. Then since he has a lot to do with set theory, we'll see what a set is. We'll look at one-to-one correspondence. This is how you can compare two things in two different groups, such that you can determine various characteristics between the two groups. And then we'll move into Galileo's paradox. Actually, the first time I saw this was several years ago. This thing blew my mind. And then I'll look at counting even numbers, all the integers, rational numbers, and we'll move into a piece of real estate that David Hilbert invented. He has hotels, but these hotels are infinite. And we'll look at some conditions and what happens when you look at these infinite hotels. And then I'll explain the diagonalization argument invented by Cantor. And this diagonalization argument has been used by Turing as well as Goethe on some of their work. I'll go into space filling curves and then look at power sets, which are subsets of a set. And then we'll take a look at Cantor's continuum hypotheses and Russell's paradox. And then we'll finish off with a conclusion. So Cantor was born in St. Petersburg in 1845. And when he was 11, his parents moved to Germany. And in grade school, or I guess high school, they found that Cantor had mathematical skills. And in particular, it was towards trigonometry. And he was able to solve some trigonometrical problems that even the top-ranking professors at the university weren't able to do. He received his degree from the University of Berlin, his doctorate in 1867. And one of his professors that taught him was Leopold Kronecker. And although he was a teacher then, he was going to be a future nemesis. So Cantor, after graduating and getting his doctorate, he went into, he made his first paper in 1874 on innumerable sets. And that particular paper he did while he was at the University of Halle. And this was actually the start of his paper writing career. But what he managed to do in this paper was count rational numbers and count and enumerate algebraic numbers, which are the solutions of polynomials. With this, he was able to determine the cardinality, or the size of these sets. And in 1874, the same year that he made his first paper on set theory, he got married, went on a honeymoon into the mountains in Switzerland, and that's where he also spent a lot of time with Richard Dedekind. And he had met Richard Dedekind 2 years earlier. And I guess every time they would go into the mountains, he would meet with Richard, and he collaborated with Cantor on some of his set theory. But eventually, Richard got a position outside of the University of Halle, so Cantor lost his good friend. And he always wanted to go back to the University of Berlin. After all, that was his alma mater. And University of Berlin had a number of teachers that or professors that were well known in the field of math. But because of his paper and his work on transfinite numbers and trying to count rational numbers, real numbers, it upset the status quo within the mathematics field. And when he tried to apply to the University of Berlin, Leopold, his nemesis, always knocked him down. And Leopold went so far as to call Cantor a renegade and a corrupter of youth. And these are fairly insulting terms back then. Today, there may not be so bad, but he was under constant struggle of the introduction of the ability to take a look at these transfinite numbers and to be able to enumerate them and compare them with the natural cardinal numbers. That it was a very difficult battle. A lot of people weren't accepting his work. And here he also lost his good friend, Dedekind, but he managed to pick up a new friend. And that was Augusta Mittag-Leffler. So between the years of 1874, when he made his paper here, to 1884, he had 10 good years of paper production. And he was friends with Leffler. Leffler ended up being a very rich individual. He had his own mathematical journal called the Acta, and Cantor used to publish in his paper. And he was also very close friends with Leffler. And during their friendship over the years, there was over 50 personal letters that Cantor sent to Leffler. And in all of those letters, over 50, every one had the mention of his nemesis, Leopold. And he was very upset with Leopold because Leopold wouldn't accept his work. And it put him into basically a depression, and he ended up going to the sanitarium. However, even under this duress, he managed to get involved in the committee to form the International Congress of Mathematics. And this is a dominant conference in the European field, where in 1900, this is where David, I just lost his name, Hilbert.
Hilbert.
David Hilbert gave his paper of 23 problems. However, in 1902, I think it was, Julius Koenig, a Hungarian, provided or gave a paper at the International Congress of Mathematics in 1902, basically saying that Cantor's transfinite numbers and all of his work is false. And this in particular affected Cantor because his daughter was in the audience, and he looked at this as a personal insult, and it added to his already constrained mental state. But the next day at the same conference, Ernest Zermelo, who's shown here, and he worked with Frankel to make a new set of rules for the set theory, gave in his talk a description of how Julius was wrong. So Julius had his day, the previous day. The next day it was destroyed by Zermelo. However, for Cantor, now he was going into the sanitarium every couple of years. And eventually, in 1918, like all of the greats, like Mozart and Cantor himself, he died in poverty and in the sanitarium of a heart attack. So he struggled to get his ideas in, and in 1925, David Hilbert wrote a paper on the infinite. And inside this paper, he stated, "No one shall drive us out of the paradise which Cantor has created for us." And in that same paper, he said, regarding the theory of transfinite numbers, this theory is, I think, the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. Basically, Cantor carved out a new field in mathematics called set theory. So what is a set? And according to Cantor, a set is a collection into a whole of definite, well-distinguished objects of our perception or our thought. A set can be classified as having components that are finite, or it could have a set of components which are infinite. So some examples of sets, and sets are shown by the enclosure within the curly brackets. So let's say I asked for the set of vowels. We would have A, E, I, O, U, and enclosed in curly brackets. So that's a set. You could have all the odd numbers less than 10. So here we have a set 1, 3, 5, 7, 9. And if you look at the two sets of the vowels and the odd numbers, you see that they have a cardinality. The cardinality is the size of the set. Their cardinalities are equal. So the set of vowels has 5 elements in it, and the odd numbers has 5 elements in it. So these two sets have the same cardinality, and we'll be using that term later. Of course, you can have all the even numbers, 2, 4, 6, and with the ellipse that goes on forever. You can do the odd numbers, the prime numbers, but one of the important ones is a very important enumerable set, which is called the natural cardinal numbers. These are the cardinal numbers that we're familiar with, where we do counting and we enumerate things. So we have 1, 2, 3, and it follows the order of succession. This is a very nice set because we understand ordering and we understand the count of things. Now, if we take a look at a subset of this natural number, a subset is another set that's derived from the primary set. And for instance, on the lower left, I have the set 1, 2, 3. That is a subset of the natural numbers because those numbers are included in the natural numbers. But 1, 2, 3, the order isn't very important. It's equivalent to 3, 1, 2 or 3, 2, 1. So this is an interesting point about sets. You can rearrange the objects in the set to have a particular order, and that order may be very useful for you in order to do comparisons. So let's take a look at some mappings first, because this will help us introduce ourselves to one-to-one correspondence, which will be a very dominant feature that Cantor developed and combined it with these infinity sets. Here we have a set on the left, N, and a set on the right, S. So let's say the set N are the natural cardinal numbers, for example. And I want to take a look at the subjects of one-to-one and surjection. And I want to see how one-to-one and surjection plays itself when we start matching up set N to the set S. So if we look at the top left, 1 goes to E, 2 goes to A, but I missed D. And so I do have the property one-to-one because only one item from the left goes to one item on the right. But I don't have it surjective. Surjective means I covered everything. Well, D has not been covered. So this figure basically has the properties one-to-one, and it's not surjective. Well, let's take a look at the reverse case, which is shown below it, where we have the condition of it not being one-to-one, but it is surjective. So if we take a look, everything on the right on set S has been covered. So it has a surjection. However, if we take a look at B, both 3 and 5 point to it. So it's not a one-to-one. So we've looked at the two opposing aspects of these properties of one-to-one and surjection on this page. Now here, let's take a look at the condition of not having one-to-one and not being surjective. So when we start mapping from the left to the right, from the N to the S, we see that we don't have everything covered. D is not covered, so it's not surjective. And furthermore, C happens to be pointed to by 4 and 5. So this is not a one-to-one. If we go below, we see what we really want to achieve. And we want each one of N to match to each one of S. And we want to make sure that S is all covered. So here's a case where we have the one-to-one, and it is surjective. This is the basis for one-to-one correspondence. And that is, each element of set N is paired with exactly one element of set S. Each element of set S is paired with exactly one element of set N. Therefore, those arrows are pointed on both ends. So we can go either direction. We only have the property one-to-one, and everything is covered. It has the property of surjection. When it has that condition, it's known as a one-to-one correspondence or a bijection. And we'll be talking about one-to-one correspondence in the future. Now, one-to-one correspondence is actually a very old technique. And there was a native tribe in Australia who couldn't count past 20, but they wanted to vote in a new chief every so often. And the chief would have a large number of cattle. And they couldn't count past 20, but the chiefs that were competing to be chiefs, because they were sort of like running on a political basis, their winning was going to be by taking a look at the size of their herd. Whoever had the largest herd became chief. So with two competitors, competitor chief A, competitor chief B, they would take their herds and then bring them together and pass one of the cows from one of the herds and a cow from the other herd through a gate. And they would keep on doing this. And eventually one of the chiefs would have a bunch of cows that were depleted, and one chief would have a cows that would be left over. The one that was left over was declared the chief. And what they did is basically they did a one-to-one comparison. And the number of cows could have been hundreds, but they didn't have to count. It's sort of like putting your fingers together and they match. And you don't even have to count how many fingers you have. So this one-to-one correspondence is a very ancient technique, but it's also a very powerful technique. And when you have this one-to-one, you want to be able to do enumeration. You want to somehow be able to count. And one of the best counting numbers we know of, the cardinal numbers, the natural numbers, they have an order of succession. We're very familiar with 1, 2, 3. And this gives us the ability of counting. Well, this is a good enumeration set that Cantor ended up using. And it also gives us an idea of the cardinality, because if the natural numbers fit whatever set we're trying to match, they have the same cardinality. So if we do match to some infinite set S, and we match and we find that it has a cardinality of n, then S is countable, and we call it countably infinite. The set S is countably infinite if it can be counted against the natural numbers. And this particular cardinality of S, if it has that property, is called Aleph null, and the symbol is shown there. So we would say that if you were able to enumerate set S with the natural cardinal numbers, we would say it has a cardinality shown by S between the straight lines equals Aleph null. And that's its cardinality or size of that particular set. So let's look at a paradox. So when I looked at this 5 years ago, 5 or 6 years ago, I got blown away by this. But let's take a look at it. Along the top, I have the natural cardinal numbers, 1, 2, 3, 4, 5, and so on. Now, what Galileo did is he built a set, but the set only contains squares. So the set contained 1, 4, 9, 16, 25. And Galileo used the technique of one-to-one correspondence. Now, it's kind of interesting. You see that the squares are a subset of n. Furthermore, if you take a look at n, it contains not only the squares, which are shown in red, but it contains all the non-squares. Yet we're still doing a one-to-one correspondence of the squares, and only the squares, to that of the natural numbers. It violates one of Euclid's rules from the elements, that the whole is greater than any of its parts. In this particular case, they're equal. The n, if we enumerate it against the squares, and even though the squares are contained in n itself, we still did a one-to-one correspondence. Galileo's paradox is bijective. It is one-to-one correspondence. We sent 1 and 1 through the gate, 2 and 4 through the gate, 3 and 9 through the gate, and everything matches perfectly. It is a countably infinite set, all of the squares that exist. The cardinality of the squares is Aleph null. Well, we can do this for the squares. If we take a look at the squares and we do a finite representation of the sets, we find that finite sets and their subset. So we have that we picked a set n, 1, 2, up all the way to 9, and we terminated it. This is a finite set. And we took a subset from this, all of the squares. But we can't match the top to the bottom. There is no one-to-one correspondence. One-to-one correspondence, when we're doing matching, does not work for finite sets. But if we go to an infinite set, like even numbers that go on for infinity, and if you think about it, the even numbers are half of the natural numbers. Yet we can arrange in the even set, which is here, the numbers 2, 4, 6, 8. We arrange them this way particularly because we make sure that we get every square, every even number. And once we have that list of E, we can do the comparison with the natural cardinal numbers, and we find that it has the property of being bijective. And that, therefore, the even numbers are countably infinite, as a countably infinite set. And the cardinality or size of the even number is, again, a left null. The same thing would happen with the odd numbers. So let's look at all integers. For all integers, we're going from the ellipse down to -3, -2, -1, 0, 1, 2, 3, and onwards to infinity. So we want to somehow match the natural cardinal number set with a one-to-one correspondence with these numbers. But you see that you have this set, you are allowed to rearrange the order. You rearrange the order to make sure that you capture each and every number in this sequence. And the way that you rearrange the order is shown here on the bottom. We'll take 0, then we'll take 1, then we'll take -1, then we'll take 2, then we'll take -2, 3, -3. And if we do this for infinity, we're certain that we're going to capture every one of the numbers that are in this set here on the top. This has the one-to-one correspondence. It has the bijection with n. It's countably infinite. The cardinality of all the numbers z is also a left null. So it's the size, as Cantor would call it, is a left null. Now we come to rational numbers. You would think rational numbers. A rational number is an integer divided by an integer, but we're not going to use the q being 0, so we'll exclude that. So q is p over q. It's a quotient, and some examples is shown here, like 1/4. 5/63 over 2,590, and 1/1,000,000. So these are examples of rational numbers. If we take a look at the average between any two fractions, we'll get another fraction which lies in between the two fractions. And if we take that fraction and compare it with the initial fraction, in other words, we take the partition between two fractions, it'll be half. Then we take one of those halves, we figure out the average, it'll be 1/4. And then we take those two. We can keep on doing this forever. Rational numbers between 0 and 1 are everywhere dense. You can always find a smaller rational number. Surely this can't be countable. But we'll see. There's a condition about rational numbers. if you take a look at their decimal expansion, the rational numbers either terminate or they repeat. So take a look at the example of a quarter. If we took its fraction, it'd be 2, 5, and then 0, 0, 0 for infinity. It terminates. However, there could be another fraction, and I made this one up, of 0.1234. 1, 2, 3, 4. 1, 2, 3, 4. This is a repeating fraction. It is a rational number. And you can always get the rational number from the repeating fraction. And if you take a look at the repeat, this is tens, hundreds, thousands, 10,000 position. So if I multiply x by 10,000, I move the decimal point over 4 positions. And then from this, I'll subtract x. And x, what I'm subtracting is its fractional component. And I'm left with 9,999x equals to 1, 2, 3, 4. And here's the fraction. So repetitive fractions and fractions that terminate are characteristics of rational numbers. So how do we count all of those rational numbers? Well, we'll take a look and we'll form a row. And in the first row, remember, I'm going to put all of the integers along that line. So remember, I had 0, 1, -1, 2, -2, 3, -3. This way I get all the positive, all the negative numbers. And on this row, I divide everything by 1. Now, the next row, I use the same numbers, 0, 1, -1, 2, -2, 3, but this time I divide them by 2. The next row, I divide by 3. The next row, I divide by 4, and so on to infinity. And so now I have this matrix. And remember, I want to make a set, but I pick the order that the set has. Now, why do I want to pick an order? Well, I want to pick an order of extracting out these rational numbers in a fashion that I ensure myself I captured each and every one from now to infinity. And so we follow a pattern. And this pattern, if we follow it religiously, we'll be able to cover this entire matrix. And as we're doing this, we're making a 1-to-1 correspondence with the natural cardinal numbers. So we start with 0 over 1. And 0 over 1 is shown here. And it's building up in my set, 0 over 1. I come to 0 over 2. It's repetitive. In a set, if it has the same value as previous, you do not count it. We go over to 1 divided by 1. That comes down here and it makes it into the list. The next number is -1 over 1, and that makes it here into the list. We come down to 1/2. That makes it into my list. We come to 0. We bypass it. We already have a 0. We come to we bypass it. If we get to the third, we find that we add the third in. The next one's -1/2. 2, -2, these show up here. We get 2 over 2. We already did a 1. We exclude it. We get a -3rd and so on. So we can take this matrix that's shown here and through an algorithmic flow through this matrix selected by Cantor, he ensures that he covers all of the fractions. And by putting it into this list, he can do a 1-to-1 correspondence with the natural cardinal numbers, and he maps all of the rational fractions to the natural numbers, and he sees that the cardinality or the size of these rational numbers is the same as before. It's Aleph null. This is quite an amazing result. And set theory lets you reorganize the elements that are in your set to your advantage. And you could leverage that advantage to start counting all of these strange numbers, sets of numbers. Now, what about algebraic numbers? Algebraic numbers are roots of the polynomial of different orders, where a to the n does not equal 0, and we'll even make the additional condition that it's greater than 1 or 1. And all of the AKs are integral rational numbers. And in such a polynomial equation, there's something defined of a height, and it has to do with the components that are within the polynomial equation. But this height can be determined for each one of the orders of the polynomial. And by adding all of these heights together and putting them on paper, you can compare them with the natural cardinal numbers, and where these algebraic numbers are the roots to the equation, and some of them might be the golden ratio, 1 plus I, all of the integers, all of the rational numbers and their roots. He found that, and this is in his very first paper in 1874, he found that the set of all algebraic numbers is enumerable. It has a size that's just like the rational numbers, just like the even numbers and the odd numbers and the square numbers. It's Aleph null. So now we're going to move into Hilbert. He was in the real estate business, although people say he used to be a mathematician, but he was in the real estate business. He had hotels that were filled to infinity. Now, these are not hotels where you and I may own, which only have a finite number of rooms. And if our hotel is completely full, we cannot take a new guest. However, Hilbert's hotel is different. A new guest comes in and Hilbert says, no problem, I'll collect your rent. I'll tell you what I'm going to do. First of all, my hotel rooms are countable because I put numbers on them, on the doors. Number 1, 2, 3, 4. This kind of looks familiar to our natural cardinal numbers. So we've numbered the doors. And then I can start giving instructions to my guests. And the instruction that I give to my guest is I tell each guest to move to the room, one room higher. So 1 down here says, all right, I'll move to 2, and 2 moves to 3, and 3 moves to 4, and so on. And we have an empty room in 1. So Hilbert can collect the rent from this new guest, and as he goes into room number 1. But what this rule says is that we have Aleph null, and we add 1 to it, it makes Aleph null. So we can always add 1 to Aleph null, and it's Aleph null. And we can keep on doing this. Matter of fact, Hilton has an infinite many guests that arrive. His infinite rooms are all full, but he can still fit all of his infinite guests. What he instructs his guests to do is whatever room you're in, move to a room that's 2 times higher. So 1 moves to 2, and then 2 moves to 4, and 3 moves to 6. So now we start emptying out all of the odd rooms in Hilbert's hotel. And when all of the odd rooms are emptied, Hilbert says to his infinite guests, and of course he will collect rent. He's very happy here. And he tells all of his new infinite guests to occupy all of the odd rooms in the hotel. And they fill up all of the odd rooms, and now Hilbert's hotel is full again. So what this says is that alpha sub aleph null plus aleph null equals to aleph null. So this infinity is quite a strange number. Now, Hilbert made a lot of money selling to those infinite guests. So he actually built another Hilbert hotel, and it was empty. And he goes, but how am I going to fill it up? So he says, all right, everybody in the odd rooms, go out and fill up my empty Hilbert hotel. And now with all of the odd rooms empty, he instructs the individuals to whatever number room they're in, divide by 2. So then 2 goes into 1, 4 goes into 2, and he refills his initial hotel. So now, by these two-step processes, he has filled all of his hotels up. Unfortunately, I don't think he made any money here. Now, we've looked at a number of different set of numbers, but there is a set that we haven't looked at yet, and it's the irrational numbers. These are decimals that do not repeat and they do not terminate. They cannot be expressed as a ratio of 2 integers, because if they were expressed as a ratio of 2 integers, they'd be rational. Now, we're going to say that between 0 and 1, we're going to collect all of the numbers, all of those decimals that are non-repetitive and do not terminate. And then by the proof of contradiction, we'll assume that they can be enumerated, but will show otherwise. And this is one of Cantor's famous mathematical techniques called diagonalization. So this is his diagonalization argument. This argument proves something here that we'll get into, but this particular argument has been used by Turing as well as Gödel in their proofs. So this is a fundamental type of an argument. Now Cantor is saying, I want to enumerate against the natural cardinal numbers shown here of 1, 2, 3, 4, 5, and onwards. On each one, I'm going to put one of the numbers, the real numbers that I have between 0 and 1, and I'll assign it there, and I'll make a 1-to-1 correspondence. Then I'll take my next number and assign it to 2. And he lists all of his numbers down to infinity. And he says to himself, I have got all the numbers. And he feels very happy about himself. And then he thinks about the diagonalization argument that he developed. And what he wants to do, his goal is to construct a number z that's not in this list. So this z will be 0 dot positions z1, z2, z3, z4. And he goes, what am I going to fill these positions with? He goes, I know, I'm going to take this diagonal all the way to infinity. So on position 1, he looks, he has the number 6. So when he fills the number in this position that corresponds to the cardinal number 1, he changes the number from 6 to another number. It has to be something different. In this case, it's 1 higher. This number here, z equals 0.7, is definitely not this, and cannot be this number. Then he goes to the next number and picks the second one on the list, 8. He brings it down, changes it to a 9. This number, 0.79, is neither in this line or in the second line. And we can continue doing this and build up this number from the diagonals where we change the value that exists there. So if we take a look at 68139, I changed it to 79240. This number Z is not in this list. We did not enumerate the natural cardinal numbers N with the real numbers. We did not do it. And we can take this new number, put it at the end of the list. We can repeat the process. We'll find another new number. We cannot put the real numbers in a one-to-one correspondence with the natural numbers. The real numbers are uncountably infinite. They're beyond alpha null. The cardinality of the real numbers is given another term. It's called C for continuum. C is the cardinality of the continuum of real numbers. So C is much larger than alpha null. And then we have transcendental numbers. Well, where do you find transcendental numbers? Very easy. You find all the algebraic numbers in the real numbers. You can make a Venn diagram of it. Whatever's not inside the algebraic number, and that's within the real, is a transcendental number. The transcendental numbers also, because they have fractions that do not repeat, they do not terminate. The set of all transcendental numbers is non-enumerable. The cardinality of the transcendental numbers is denoted by, again, C, the continuum. So the size of the transcendental numbers is huge. Now we can move into space-filling piano curves, where we saw that the number of numbers, real numbers between 0 and 1, all of these numbers has that cardinality of the continuum, C. And this is in one dimension only. Cantor said that you can go into 2 dimensions and cover an area. And so somehow you should be able to map from this linear 0 to 1 into a 0 to 1 in a unit square. And if you could do that, they have both the same cardinality. There's nothing different about it being a square, having another dimension. Matter of fact, it can go into multi-dimensions and it still has the same cardinality of C. But Giuseppe Peano discovered a continuous space-filling curve, and he was motivated by Cantor. And he showed that they have the same cardinality. Matter of fact, this is the definition of a space-filling curve. It's a curve with endpoints that is a continuous function whose domain is the unit interval 0 to 1. So we have 0 to 1 on a straight line, and we can somehow make a curve, which we'll have to see what it is, that will fill up this unit square. Hilbert illustrated Peano's discovery. Now, these squares are shown like they're increasing in size, but the area is all one. They're only getting magnified so you could see what's occurring inside. And so what Hilbert said on his very first area, it would have a line that goes through both X and Y dimensions. And this line starts at a 0 and it ends at a 1. And it has all of the numbers, the real numbers along the line. What he does is he basically kind of magnifies those little numbers into the smaller numbers. And then he arranges this fundamental shape different ways of mirror imaging and rotation, and then he connects them together. And again, you start from 0 and you end at 1. And you do this again. And now it's 8 squares on the side, 16 squares on the side, 32 squares on the side. The points in this unit interval map to an area in the unit square. It's an unenumerable set, but it's the same size as the set of that number on the linear line. And here's an example of how it might grow. And this could continue on and on until you fill up that whole square. And the numbers that are there is C, the continuum. Next, he went into power sets. So a power set, let's define what a power set is. We can have some set that contains ABC. The cardinality of this is 3. The power set is the set of all subsets of S. So every set contains the null set, which is here. So here we start building up the power set. And we show that it's a set with these curly brackets at the end. The first thing we put in there is the null set. And then this has an A, we put it in. It has a B, it has a C. You can also connect another subset of AB and a subset of AC, BC, and finally the set itself. If you look at this, this is 8, and we have 3 components. We see that the cardinality of this power set is 2 to the 3rd, because we have 3 elements. We can extend this to the cardinal natural numbers. So we want to know, what is the power set of the cardinal natural number? We'll see that it's 2 to the number that we've been dealing with all of this time, Aleph null. And it ends up that 2 raised to that power is equal to the continuum. So the continuum is a huge number. The continuum, which is the cardinality of all the real numbers, is 2 raised to the power shown there. Now you can take C and raise it. You can do a power series on the power series. It will get a huge number, and you can continue doing this. You can get an enormous infinity numbers. But let's take a look at the continuum hypothesis that Cantor proposed. And this was actually the very first problem that David Hilbert gave in 1900. It was show that there is a continuum hypothesis. And what is it exactly? Well, we've seen that there's a cardinality of the natural numbers. It's alpha, Aleph null. There's a cardinality of the power set, which is the continuum, and it's 2 to the Aleph null. The cardinality of the real numbers is the continuum, C. So he asked, Cantor asked, is there a cardinality strictly between Aleph null and the one that contains the size of all the real numbers? Is there some A cardinality that exists between this and this. And so far, it hasn't been solved. Now we're coming to the end of the talk, and we're going to take a look at Russell's paradox. Now, Frege, Gottlieb Frege, shown here, was writing a book, Foundations of Arithmetic. The basis of his book, he used naive set theory. And this is the same theory that Cantor used initially, and everything was good. It was good until Bertrand Russell showed up. Bertrand Russell managed to get a copy of Frege's book, The Foundation of Mathematics. And Russell showed him that the basic law, number 5, in the foundations to be false. Now, all of the laws that Gottlieb used in his book, it all rests on the foundation of set theory. But so if set theory is perturbed, Frege's book will probably have to be amended somehow. So what is this problem with the naive set theory? Well, remember, whatever you can think in your mind, it's an element. Anything you want can be comprised of a set. So let's take a look. Naive set theory allows the use of any property to form a set. So you have absolute freedom. But let's take a look at a set of integers. It's not an integer. The set itself is not an integer. It contains integers. And if you look at the top level, it's not a set. So it's not a member of itself. This set of integers is not a member of itself. But we can, through our mind, and what Russell did is he said, well, let's get a set of all sets. And that set is a set. So there are some sets which can be members of themselves, but not all sets satisfy this in the naive set theory. So Russell here on this line, he says, let R be the set of all sets that are not members of themselves. Now already this starts twisting your mind because wait, there's something wrong here. There's something wrong here because if R is not a member of itself, but its definition entails that it is a member of itself, something funny there. On the other hand, if R is a member of itself, then it is not a member of itself since it is the set of all sets that are not members of themselves. So here you have a contradiction. And this contradiction Russell sent to Frege and when he was doing his second edition. And unfortunately, it's much to the chagrin of Frege. And it changed the naive set theory to the Zermelo-Franco theory with the axiom of choice. And so they had to change the rules of set theory. And based on what's his name? Gödel and his incompleteness theorem, that even though you have these new rules that avoids Russell's paradox, because of the incompleteness theorem, we're not certain that even the Zermelo-Franco rules are going to withstand agony and torture in the future. There may be somebody in the future that finds something that violates it, according to Gödel. So, in conclusion, we see the natural numbers, 1, 2, and 3, 4, have a cardinality of alpha null. All of the square numbers have the same cardinality. I didn't do the prime numbers, but you could imagine putting the prime numbers into a list. You'll find that it has an alpha null. All of the even numbers, all of the odd numbers, all of the rational numbers, and all of the algebraic numbers are countable to alpha null. The irrational numbers, which are non-repeating decimals, and the transcendental numbers have the magnitude of the continuum. And all of the real numbers have the magnitude of the continuum. So I've shown a Venn diagram, and the outer circle is all the reals, and contained within is the rational numbers. And within all the algebraic numbers, you have all of the rational numbers, all the integers, all the prime numbers, and you have it inside of the algebraic numbers. Everything outside of the algebraic number is a transcendental number. And we only know a few that we use to do various things. I wouldn't be surprised if there are numbers that are discovered that are constants for some phenomena that we're not aware of yet. But that number that we need, if we do need it, is going to exist in this transcendental list. This is some of the material that I used for today's talk from Wiki. This is a reference of the books that I've used. And this is for you. Thank you for listening. But that concludes the talk. And if you have any questions, let me know. Thank you.
Okay, thank you for that talk, Thad. If you could stop screen sharing for a moment, we'll get the questions and answers.
All right, now let's see. All right, so did I manage to do it?
Yes, you did. Okay. For those that have a question, would you use your symbolic hand, which is raise hand at the reaction button. Mark Edelman is the first.
I enjoyed this so much. Thad, you are a terrific, absolutely terrific teacher.
Oh, thank
you. Really, I mean this so much. Everything you said was crystal clear. And you took us through the steps in a beautiful order. And even your slides were always exactly what they needed to be. And I'm scheduled to present next month, and my presentation won't be anywhere near as good as this one. So I just want to pay you that tribute, because I think this was an absolutely outstanding presentation. And now let's get to all the questions and criticisms.
Okay, Bill Heary, you have your hand raised.
Yes, very good talk. I enjoyed it a lot. I knew all the mathematics for a long time, but it was interesting to get more of the historic perspective on how things fit together. So I really enjoyed that. I do want to comment, though, on the continuum hypothesis. It actually is sort of a settled problem if you believe or use the Zermelo-Fraenkel set theory. I think it was about 1935 or so, Gödel proved that you could not prove the continuum hypothesis from within the context of Zermelo-Fraenkel set theory. And sometime in the 60s, I think about 64 or so, Paul Cohen proved that you can't prove it. So one said you can't prove it, the other said you can't disprove it, which made it a formally undecidable statement in the Gödel sense in Zermelo-Fraenkel set theory. That means that it is, you've shown that you can't prove it, you can't disprove it. There's really no answer in ZF. Therefore, if you wanted to, you could take that as an axiom and build an extension of ZF, or you could take the opposite of it, that there is something and you use that as an extension of ZF. So it really is a solved problem in ZF. As you pointed out, though, who knows if ZF is going to stand up forever as an acceptable set theory.
Oh, well, thanks for that clarification, Bill.
Yeah. One other question that I have for you, or maybe you do or don't know the answer. I know that Cantor chose Aleph, which is the first letter of the Hebrew alphabet. When I was a student, it was always pronounced Aleph. You are pronouncing Aleph. I suspect it goes back to the Hebrew, which I don't know. So do you know what the proper pronunciation is?
So how would you say it again?
Well, when I was a student, they always said Aleph.
Aleph. Okay.
But I don't know if any of the teachers that I had knew Hebrew.
All right.
You're using Aleph, maybe you know Hebrew and that's where it comes from. Well, I just was curious if you know what the proper
Well,
pronunciation.
that's what I actually used pronunciation on the web to tell me what it was.
Okay.
So they were then they could have been wrong.
Yeah. The web is never wrong, right? Okay. So I'll have to actually dig into that then. I never thought of that question because I always heard it pronounced Aleph.
Me too.
Thank you.
I've heard it many times. It's Aleph.
Actually, I've heard there's also Aleph 1 and Aleph 2 or something like that, but
Yeah,
it wasn't in the
those
talk.
are the powers of Aleph. 2 to the Aleph null, Aleph 0 is Aleph 1. 2 to the Aleph 1 is Aleph 2. It's you could build a whole chain of higher and higher orders of infinity.
I see.
Yeah, that's the
Okay.
power of the power series of the power series of the power series.
Exactly.
Okay.
I just checked my my magic dictionary that has almost everything in the world, and it says the pronunciation is Aleph. Accent on the first syllable.
Oh, I watched that show once in a while, Alf.
It was good, yes.
Okay, John Maheda, you have a question?
Yes. Do you hear me?
Yes.
Yes.
Okay. Wonderful talk. I'm blown away by it. One question. Is my understanding correct that all of the elements of a set have to be unique, have to have unique values or unique properties?
That's correct. So if there is a set, let's say 1, 2, 3, 1, you have to reduce it to 1, 2, 3. You can't,
Okay.
there are no repetitive elements inside.
Right. Okay. So if I have a set which has itself as a part of a set, I am therefore running into a situation where I have basically non-unique values, because I have the set which is a part of a set itself has the same values as the original set.
Now, I don't know how they managed to put that removal within the rules of naive set theory. And it may be that that rule wasn't well specified. And
Okay.
so, you know, having the set of a set of a set, you know, it sort of says, gee, you're almost doing the same thing. But maybe, do the sets have to be the same if you're combining a number of sets?
Well, it would,
Just be sets of sets that are sets of different things, but they're all sets.
Well,
And have a set that contains all of those sets. So you might be able to wiggle in a slight change in that paradox.
okay. Because otherwise you would be saying basically the set cannot be part of itself.
Within a set, there is no duplicated element within.
Every set
This
is
is
unique.
he did like a fantastic thing, and once this in the beginning, he had a tough time getting this accepted. As a matter of fact, it was put a great strain on him. But into the 1900s, the early 1900s, they found many applications for the set theory, and Frege was going to use it to develop basic mathematics all the way from the beginning, because you would have in your set the counting numbers, and then that leads on to all of these kind of crazy things. He opened up this field, and today we have a better understanding what infinity is.
Well, that kind of follows up what I was going to ask. Theoretical physics is fraught with all kinds of infinities. And is a set theory used in theoretical physics? Are you aware of that?
I'm not aware of it. I know they use it in topology, but I don't know if it's used in physics. How does it work where the components keep on breaking up, right? An atom into its components, protons, neutrons, and neutrons breaking up, and then even those components, and they could continue breaking up. So how do you apply the set theory to that? I'm not knowledgeable enough to know that.
Thank you.
Okay. Are there any other? Mark, you have another question?
Yeah, I just want to mention that I believe, I am not in any way an expert on this, but I believe that Russell spent a lot of time clarifying John Makeda's question. A set that is a member of itself, okay, that the set is not the number. You always have to make that distinction. So for example, a set that just has the number 1 in it is not the number 1.
Correct.
And that is the reason that's the distinction that allows you to get through this puzzle about sets that contain themselves. When you say it's a member of itself, the grammar is very confusing. But when something is a member of itself, that is not an identity. Something is not itself because it's a member of itself. Okay? Being a member of itself doesn't mean that it's the same thing. It's still a different thing. So take that for what it's worth. I don't know how to explain it any better.
Well, it's a riddle wrapped up in an enigma.
Okay, Bill, here you have another question?
Yes, I think I can try to clarify that point. You have to distinguish between something being an element of a set and a subset of a set. So if you just take the simple case of a set consisting of 1 and then another set of brackets, the set consisting of 1. So it's I don't have a board type, but open brackets 1, comma, open brackets 1, close bracket, close bracket. 1 is a sub 1. The element 1 is an element of the first set, but it's not an element of the second set. And I think the confusion comes from trying to look at a string of these sets put together and looking at the elements of all of them together, which is not the same thing as looking at what sets of sets there are. Okay, so if you took the set, 1 and the set of 1, that's a 2-element set. 1 is an element of that set. So but it's also an element of that. So it's really distinguishing between element of and contained in as a proper subset terminology. I don't know if that clarifies things.
I think so.
This is why we had Bertrand Russell, right? He wrote this big book on this.
Well, what he was actually trying to do is derive all the mathematics from what we would now call naive set theory. And then he found that, whoops, it's not going to work. And that started a lot of other things going that eventually even led to what Gödel was doing.
Yeah, and it made that Zermelo-Frankel theory.
Right.
And,
Well,
from what I
Zermelo-Frankel came
understand,
after.
yeah, from what I understand on that theory is that they constrain the definition of what the set is, but any subset from that set can be anything you want. So there is a freedom in the Zermelo-Franco, that the subset itself can be anything you want, is my understanding. And that's where the anything you want has to go to the subset of the set, but not the set itself. The set itself has to have a very certain definition to avoid that Russell paradox.
Well, the definition is, it's not quite as simple as a definition. What they established is a hierarchy of classes, and you can't mix the classes of the set. So the set of all sets would be a higher class, and that's you put that in to avoid having these things happen. And
This is
many people think it's a kind of artificial construction, but
This
that's
is the man commenting.
Is he a summit guy or just a guest?
I guess he's a guest.
Okay.
Yeah.
all right. So anyway, but Zermelo-Franco did more than what Russell had done in trying to fix the problem. He came up with the idea of classes, but then he got so frustrated with it that he left mathematics and went to philosophy. And he's better known to most people as a philosopher. And if you're old enough, you might remember him protesting the Vietnam War during the Vietnam War days when he was in his 90s and getting arrested in his 90s. Very interesting person. But he gave up math in the early 20th century.
Right. Well, I think he passed away in 1970, so it's
Right.
within our lifetime for sure.
Right, and I remember news stories about him being arrested for protesting the Vietnam War. I think it was in Sweden or someplace like that where he was.
Plus, he won a Nobel Prize for literature, so he's
for a book on philosophy.
yeah, an all-around guy.
Yeah.
Okay, Mark, you have another question?
Yeah, Russell started protesting in World War I,
Right.
and he kept on. He was a pacifist. But the thing I really wanted to say is just a remark that something that is, to me, very interesting is the fact that, you know, the theories of infinity were used and led to further thought by Turing and by Gödel and so forth. But meanwhile, in a computer, the only numbers that really work in a computer are the natural numbers. I mean, you can represent anything you want in a computer, but what's in there is the natural numbers. And to me, this presents some mystery and some puzzlement because, you know, you're using the natural numbers to represent things that may not even be numbers, right? And this relates to your talk about, you know, mapping and correspondence, one-to-one. The miracle of it is the idea of representation. Mapping and representation are pretty much the same thing. And so I just wanted to say that because it can lead you in a lot of directions.
So we can take that computer example, for instance, of having a stream of bits. And this long stream of bits is one of the real numbers, but it can't go on. The problem with the actual machine is you can't go on to infinity. You have to stop someplace.
Well, you can't put a real number in a computer.
Yeah, you can't. And that's why, because it would have to go to infinity. And this binary stream of ones and zeros that goes on to infinity to try to represent a number can't be done. So we are limited somehow. Yeah, that machine puts a constraint on Cantor. And I guess it introduces interesting problems in the computer world where compilers try to compile other compilers. And all sorts of crazy things could go wrong.
Okay, George, you have a question?
Yeah, well, just to address Mark's question, I think you can use set theory to approximate the round-off error when you're doing the computational models. But anyway, my question is, the number that seems to be always left out of set theory is the denominator 0 number. And in physics, that's the number that gives us headaches. As you know, if you look at the simple equation of Einstein's relativity, the denominator goes to 0, which means that you can't go faster than the speed of light. Now, how can, in physics, what they do is they say, okay, well, we have to bring in quantum mechanics. And then you can show that you can have tunneling between an infinite barrier. So then how can, I guess, set theory be addressed to quantum mechanics?
Well,
You want the answer?
No. Some thoughts on that.
We don't have the answer here.
No, but if you look at it, because quantum theory is stating that waves, which can be thought of as an infinite set, are being represented by a particle, which is a finite set. So it's mapping the wave to a particle.
That's interesting what you said, that a wave could be thought of as an infinite set. I mean, before this discussion started, we were gossiping about some of that. And, there's no infinity in the physical world. There's no physics of infinity. But yet, when we do physical theories, like theories having to do with waves, you pretend that there's continuity, which means that there's something infinite in there. You pretend it, but there's no physical basis for that.
Well, yeah, I agree that mathematically you're limited in physics. And what we're doing mathematically is trying to represent the physical world, which
But you should say it in the reverse. The physics is more limited than the mathematics. In mathematics, you can have infinity. We've just heard all about that.
right.
But in physics, there's nothing infinite. There's no basis for it. And there's no basis for continuity either. And when I do my presentation next month, you're going to hear more about that. But there's the idea that you could take something and keep on dividing it into smaller and smaller pieces forever has no physical basis.
Well, the question is, what is a photon then?
Well, a photon certainly isn't infinitesimal.
Or is it? It's a wave of energy.
Well,
A photon
okay.
has no.
You can't divide a photon.
Right. So therefore it's infinite if you can't divide it. It's the 0.
I guess this is a discussion we'd have to have somewhere else.
I would say,
Again, it gets back to the n over 0 problem.
Now, since a photon is a particle, it's not one of those that's comprised of quarks, is it?
No. it can be thought of strings, but they're still debating that one. I don't know, John, do you know of whether string theory can represent a photon?
I have no idea.
I think we have to keep in mind also that our physical theories are always a representation of reality. They are not the reality. And some of the comments that Mark was just making remind me of Zeno's paradox. And I won't go into that lest Mark is going to include that in his talk next month.
Oh,
Well, Zeno's paradox, for anyone who doesn't know, is that the arrow which is shot from the bow can never reach the target, because first it has to go halfway to the target, and then it has to go halfway from that point to the target, and then it has to go halfway from that point to the target, and we just never end. So it never gets to the target. QED.
yeah. Well, anyway, we've gotten far afield from Thad's topic, and yet it all is related because it's related through the idea of the infinite. And infinity works two directions. You know, it works with bigger and bigger and also smaller and smaller. And so there we are. That's a big puzzle.
Yeah, Aristotle said on the physical infinity, it can't happen because if there was a physical particle and it was infinite, it would fill the entire universe. So we can't have physical infinity.
So what about space?
What about black holes?
Well, physics says that space is not infinite. It all started with the Big Bang and it's been expanding ever since, so it's finite.
Well, what we see is within the light cone of things, of determined by the speed of light. So there's always things that are outside the light cone, so we can't see them. So we don't really know what's outside the light cone.
But there's nothing there.
It could be space, it could be other galaxies.
But not according to current physics.
We actually don't know if it's infinite or not. All we can see is a finite part of it.
Could you repeat that, please?
We don't know if space is infinite or not. All we can see of space is a finite part of it. It could have been infinite from the start. We don't know.
He's saying we don't know. We only know what we can observe. But of course, we don't know what we can't observe. But I'm just speaking of current theory of cosmology, which says that the universe, which includes all space, started from a point or from something very small and has expanded ever since. That's the physics of the universe that we live in. If you start talking about something outside of that, that's not physics.
I hate to say it, but it gets back to the denominator zero problem, in that with both the Big Bang theory and I heard somebody ask about black holes, they have a singularity at their center. And the question is, mathematically, how do you represent that? And it always comes down to the n over zero issue.
Yeah, and the trouble is that the singularity leads you to something outside of our universe. And
that's right, multi-dimensions.
And that isn't something we can include in our physics. In other words, the physics just doesn't cover it. That's the end of our physics. It just doesn't get there. There is no there because we don't have any concept for it. And that's one of the troubles with black holes.
By the way, earlier today, I was mentioning I got a 3-degree Kelvin t-shirt from Arno Penzias. I don't know if you could see it here.
Yeah, we can almost
Yeah.
make it out.
Let's see if I get it in closer. Oh,
No,
it's-
hold it further away. It's out of focus.
Yeah, we can't
oh,
quite.
I have
doesn't-
one on the cam- Oh, there it is.
There
Oh,
it is,
there.
it
Yeah,
is.
yeah. Now we see it. Now we see it.
Yeah, so I got this
Yeah.
from Arnold, and this is that 3-degree Kelvin. He used to give this out to people that might have done something within the research area. And I got one of these, and I have it on my hanger, and I never wore it. But I do look at it, and on it, it says, "This is the way, 3K." Not with a whimper, but with a bang.
Yeah. Oh, that's good. That's funny. I think it should have been black, though.
I don't know, maybe you got a good deal with the shirt manufacturers for red.
Anyway, does Patrick McDonald have anything to say? Does John Hoffman have anything to say? How about John Tomaszewski?
Yeah, I just like
Yes.
to go back that I'm taking a course on Mesopotamia, and what I've heard is that in their right in the tablets that they're finding that they invented zero.
Yes, he did put something in the chat. I thought if people missed it, I thought it was pretty interesting. So the Mayans had an I-like character to denote zero. Chinese used the circle, open circle. Hindus used the dot as zero.
And according to what I was reading, is that it goes back further than where they can see it actually in writing in the Hindu.
So does it go all the way back to Sanskrit?
Goes before Sanskrit. The
Well,
cuneiform.
there are a couple of very good books about zero that I've read, and I can look them up and recommend them. And they're well worth reading because they're fascinating. One of them is by David Quammen, I'm recalling, and it's called Finding Zero. And if you look it up, it's a good book. Gives tries to give an understanding of that history.
I actually, in the chat, Tom Forger mentioned something interesting. How does a clerk notify each guest to move in a finite amount of time?
Yeah, well, that's physics. That's not mathematics.
Okay, so it's physics. All right, I want to go back to whether the universe is truly infinite or not. If you go on Quora and ask that question, is the universe infinite? You'll get an answer from a guy named Frank Helly, who's a PhD in physics from Stanford University. He says, is it impossible to know for sure if the universe is truly infinite? I'm not going to read the whole answer here, but you can look it up. Cosmologists assume that there's a significant part of the universe that is outside of our observable portion of the universe, but it is impossible to say for sure that it is infinite. That's all I know about it. It's impossible to say.
Well, physicists have, thought about things as multiverses. So these are universes that exist outside of our observable universes. And they have like specific reasons for doing this. And I won't go into it, but it gets far off the field,
Yeah, well, if there's a multiverse, maybe there is, but if there is, it's not like next door. It's not like you could go outside our universe and go enter the next universe. I don't think that's the concept. If
Well,
there's a
some people-
multiverse, it doesn't mean that you can extend your knowledge into the other universes.
But there is some belief that, like the black hole that is represented behind me, that may lead to another dimension in the universe.
Yeah, but if that's true, physics hasn't got there yet. I mean, there's no theory that brings you to that. It's just it's an idea, but it's not a theory.
Actually, I've come across something that says there's a kind of correlation between our universe and what could be the inside of a black hole. So in other words, maybe we are inside of a black hole. So that, that I mean, that sort of breaks down at some level, but it's an interesting thought experiment.
Yeah.
Anyway, all right. We're at 11:47, and I guess there's a regular Zoom lunch meeting after this at noon. Is that
Right.
correct?
Right.
So this discussion can continue on that or some other topic. But, I want to thank all of you for attending, and I want to thank Thad for giving a really outstanding talk. I thought it was very clear, and I'm always amazed how many mathematicians actually got into the nitty-gritty about thinking very deeply into numbers and integers and sets and infinities and things like that. So I hereby conclude the math interest group.